It just draw a single line from left to right. Higher is higher value, lower is lower value. This is a function of x. All right. Somebody please. Okay. Thank you.
Just on the screen.
Yeah, on the screen. Just draw from left to right.
Any function.
Any function.
Okay.
So let me restart. You need to start drawing from the inside of the screen.
Inside,
yeah.
okay.
Close, and I'm going to do that again. Yeah, thanks. Nice drawing. Thank you. So as you see from the top of the screen, the time is now evolving, right? So u is equal to 1, kappa is equal to 0 as time evolves. This is the solution. This is how the solution to this partial differential equation evolves. And this is one of the ways to visualize the solution to a PDE that is time dependent, is to just evolve in time and show an animation of how the solution changes. So somebody describe how the solution is actually evolving. It's periodic, and that's because of the boundary condition I set. So another concept, boundary condition. Right, so here the domain is going from 0 to 1. Yes, 2 pi, right? 6 point something. Yeah, so that's a and in the domain I set it to be periodic boundary condition, which means whatever comes out from the right is going back from the left. Right, so the value and the derivative and second derivative, etc., on the right matches what is on the left. And other than that, how do you see the solution is evolving? It's just moving unchanged towards the right. All right, so that's actually quite interesting when situation when kappa is equal to 0. So now let's just take a slightly different situation. Let's just increase our kappa to be a little bit non-zero. So that's increasing the diffusion term to something non-zero. Can somebody come up and draw another initial condition for me? Let's go from the very back corner. Can you come and draw an initial condition for me, please? Thank you. Just start from the inside of the screen, from left to right. Nice. Thank you. So now you see something very similar, right? But if you look closely, do you see something that is not completely the same as last time? Right. So if you examine clearly what has been drawn, now you see that the shape is actually not completely the same, right? The wiggles that has been drawn on the screen now seems to be diffused, right? So the peaks are no longer as sharp as before, and everything seems to be more mundane, right, than what's initially drawn on the screen. So that's actually the effect of diffusion, and I put it as a very, very small diffusion coefficient, just to make the effect go slowly so that you can see it. And what if you increase this to something big like 1? What actually happens if you draw initial condition? It's more dramatic. If I draw something like that, it just becomes very mundane very quickly, right? So that's what happens with diffusion. So that's mathematically, it's the effect of a term that is proportional to the second derivative of the function, diffusion. So now we looked at intuitively what diffusion does. How about the convection term, right? So let's still make it a 0.001, make it a slightly diffusing. What if I change the value from 1 to something else? What do you want me to change it to? -1. Okay, let's try it. Can somebody come and draw a -1 initial condition? Please. Sure, please, come on. Oh wow, that's a square wave. Thank you. So what's the difference? Maybe it's not really noticeable, but what's the difference? Anybody notice the difference? Huh? Right, now the direction has changed, right? Instead of going towards the right, the wave is going towards the left. Basically, -1, the value of u is the speed of the advection. Having a positive value means the speed is positive, it's going towards your right. And having a -1 means the speed is going towards the left. And the magnitude is controlling the magnitude of the speed, really. If I instead of -1, I make it -100, and I can draw, I'm trying to draw the same thing. Oh, I didn't do it well myself. If I draw something very similar to what is drawn before, like a square wave, I would just see things. Oh, maybe it's too fast. You don't really see. Let me put it as -10 as opposed to -100. I think my frame rate is too low to accommodate a minus. Right. So now you can see the advection being much faster in the negative direction. If I make it +10, you would see advection going fast in the positive direction. Okay, so that's kind of that's a intuitive understanding of what's going on, right? But what's the potential applications of this equation? So this equation is usually a simplified model of some real physics. So, for example, let's start with fluid mechanics. Okay, so in fluid mechanics, that's actually a model of heat or thermal energy being carried over in fluids. So, for example, if W is temperature, right, and then U would be the velocity of the flow, and kappa would be the diffusion coefficient of heat in that fluid medium. So as you can see, the flow would carry the temperature distribution in whichever direction it goes, while the temperature gets diffused by molecular action, right? So that's what happens in fluid mechanics. Similarly, it can also describe the advection and diffusion of chemical species if you are in chemical reaction, chemical engineering, right? So of course you would actually have a reaction term that is appended to the right-hand side of the equation. But in the absence of reaction, the diffusion of the concentration of a particular species is going to be satisfying a very similar equation, right? Okay. And similarly, if you do petroleum engineering, and you can think of W as the concentration of the fraction of oil to water. Oh, I mean, it has actually plenty of, another thing, nobody here is interested in financial engineering. If that's the case, this also can describe the famous Black-Scholes equation that describes the pricing of an option. It's also actually that equation, exactly. So there are plenty of different applications.